Welcome to the Unit 9 Section 1 video on identifying exponentials.
We're going to start off by talking about how to identify exponential equations by taking a look at what they look like overall. So the table and the graph show an insect population that increases over time. You can see time is listed in the first column, population is listed in the second column of our table. And you'll notice that the population grows more rapidly the farther along we go. And it looks like the graph here on the right. A function rule that describes the pattern is f of x equals 2 times 3 to the x. This type of function, in which the independent variable appears in an exponent, is an exponential function. So you'll notice in f of x equals 2 times 3 to the x, our x is in the exponent. Notice that the 2 is the first value of our population. It's our starting population, and 3 is the amount by which the population is multiplied each day. So from the time 0 to the first day, we go from 2 to 6 by multiplying by 3. Then we multiply by 3 again to get to 18, and then we multiply it by 3 again to get 54. So a function that has this relationship where our y values are multiplied by the same value each time gives us an exponential function. So an exponential function has the form of f of x equals ab to the x, where a cannot be 0, b cannot be 1, and b is greater than 0. The reason that a cannot be 0 is if a is 0, the whole thing is 0, and we have a constant function. B cannot be 1 because 1 to any power is just 1, so therefore we would end up with a constant function for that as well. And b has to be greater than 0. So let's talk about identifying exponential equations. An exponential equation where the variable is the exponent. Okay, it is an equation where the variable is an exponent. The base cannot be 1. So here's a few exponential equations. We're going to identify if they're exponential or not. So for this first one, 3 times 2 to the x, that's the one we were just talking about. That is indeed exponential. We have 2x minus 3y equals 7. There are no variables in exponents, so this is not exponential. In fact, we know that b is linear. C has no variables in an exponent. We do have an exponent of 2, but no variables, so this is not exponential. In fact, we know that c is quadratic. 5 times 3 to the x plus 3. We do have an x in the exponent, so this is exponential. Y equals 2x minus 1. We know that's linear, so it's not exponential. Y equals negative 1/2 to the x. X is a power, so it is an exponential. Y plus x squared equals negative 3. That is not exponential. Y equals 4 times 1/3 to the x minus 2. The x is in the exponent, so it is exponential. Y equals 2 to the x. Again, the x is in the exponent, so it's exponential. Y plus 3 equals 2 times the quantity x minus 1. This is not exponential. There are no x's in the exponent. Here we have a 5 to the x, so we have an exponential. And here we have an x in the exponent, but look at our base, it's 1. 1 to any power is just 1, so this is not exponential. The graph of an exponential function features increasingly small y values on one side of the graph and increasingly larger y values on the other side of the graph. So you can see on the graph here on the right that as we go in the positive x direction, our y values are getting increasingly larger. But if we get to the left side of the graph, or where x is becoming more negative, our y values are becoming increasingly smaller. Exponential graphs follow the same general shape shown here, but can be oriented differently. It could be flipped, either horizontally or vertically, or both, but it would still be an exponential function. So let's determine if each graph represents an exponential function. A has that shape where we're increasing on the right side, but we're getting smaller on the left, so we are exponential here. B is just a straight line, so it is not exponential. C is a parabola, which we know is quadratic, so it's not exponential. D does feature an exponential curve. E also represents an exponential curve. And in F here, we have two straight lines. There's no curve, so this is not exponential. Remember that linear functions have constant first differences and quadratic functions have constant second differences. Exponential functions do not have constant differences, but they do have constant ratios. So taking a look at this table representing an exponential function, for each x, we add 1. That's our constant change in x values. If we take a look at the y values, to get from 6 to 18, we multiply by 3. From 18 to 54, we multiply by 3. From 54 to 162, we multiply by 3. So this is our constant ratio. It's the constant multiplication factor that we are going to multiply by each time to get the next y value. As the x values increase by a constant amount, the y values are multiplied by a constant amount. This amount is the constant ratio and is the value of b in our form ab to the x. So let's determine if each table of values represents an exponential function, starting with the first one here. To get each next x value in the table, we add 1. To get from 1.5 to 3, we have to multiply by 2. To get from 3 to 6, we also multiply by 2, and then from 6 to 12, also multiply by 2. So we have a constant ratio, meaning that we have an exponential function. For b, we take a look at our x values. For each x value, we are adding 2. So now we look at our y values. From negative 9 to 9, we multiply by negative 1. To get from 9 to 27, we multiply by 3. And right there, we already know it's not exponential because our multiplication factor or our constant ratio is not constant. From 27 to 45, we have to multiply by 5/3. So that further drives home the point that the ratio is not constant, so therefore it is not exponential. A set of ordered pairs is a set of x values with their corresponding y values. To determine if a set of ordered pairs is exponential, write the ordered pairs in a table format and determine if there is a constant ratio. So we're going to do that for a couple here, starting with this set of ordered pairs. Let's rearrange this into a table so we can more easily look at it. You can see that the x values add 1 each time. For our y's, from 1 to 0, you have to multiply by 0. Now, what can you multiply by 0 to get 1? Well, there isn't anything that you can multiply 0 by to get 1, because anything times 0 is just going to give you 0. So right there, that tells us we're not exponential. And furthermore, 1 to 4, you're multiplying by 4. So we certainly don't have a constant ratio, so it's not exponential. For this set of ordered pairs, again, rearrange it into a table, and then let's take a look at our x values. We're adding 1 each time again. So going to our y, from 4 to 2, we have to multiply by a half. From 2 to 1, we multiply by a half. And again, from 1 to 0.5, we're multiplying by a half. So we have a constant ratio, and therefore we have an exponential. So this actually brings up the point here that you can either multiply by the same value or you can divide by the same value, because from 4 to 2, you can divide by 2. From 2 to 1, you divide by 2. From 1 to 0.5, you divide by 2. So you need to have either a constant factor you're multiplying by or dividing by, because dividing is just multiplying by the reciprocal. Similar to linear and quadratic functions, you can identify real-world exponential situations. You can model a real-world exponential relationship by identifying the values of a and b in the function f of x equals ab to the x. So in this form, a is going to be your starting value or your initial value. Your b is going to be your constant ratio. If the real-world situation has some starting value and that value is multiplied each time step, then it is an exponential function. You do not need a specific starting value to identify it as an exponential function, however. Knowing there is a constant ratio is enough. Determine if each real-world scenario would be modeled by an exponential function. The population of town A is 800. It grows by 5% each month. Well, our starting value here is 800, and we are multiplying it by our growth. So here, you have to take 100% of what you have of your population at 800, and you have to add a 5% of that population to it. So that's going to give us 1.05 as our multiplication factor. And so it is an exponential function. The population of town B is 500. It grows by 40 each month. Since we're adding the same amount each month, we're adding 40, then adding 40, then adding 40, it is not going to be exponential. It's actually going to be linear. But here, we're just identifying that is not an exponential function. The number of bacteria in a sample doubles every hour. So here, we don't know what the starting value of bacteria is, but we do know that it's doubling every hour, which means we're multiplying it by 2, which means we know that is going to be exponential. The amount of radiation coming from a sample, given that the amount decreases by half each hour. Now, again, we don't know what the starting value is, but we know that we are multiplying it by 1/2 each hour. So since we have a constant ratio, it is exponential. The total cost of stamps, given that each stamp costs 48 cents. Well, each stamp that you add is going to be another 48 cents. So the function is linear, so it's not an exponential function. The total mass of a box of baseballs depends on the number of baseballs in the box plus the mass of the box. We can write a function for this. We know that the starting value is the mass of the box, but we know that the change is going to be +1 for each baseball. So therefore, it is not exponential. It is linear. A microbiologist started a lab culture with 25 cells. The number of cells doubles every 4 hours. We have a starting value. We know that we're multiplying it by 2 every 4 hours, so therefore it is exponential. Exponential growth occurs when a quantity increases by the same rate for each unit of time. Exponential decay occurs when the quantity decreases by the same rate for each unit of time. To determine if an equation or table represents exponential growth or exponential decay, look at the constant ratio. So our constant ratio is our b value. If our b value is greater than 1, it is exponential growth. If it is between 0 and 1, then it is exponential decay. A graph representing exponential growth will increase from left to right. A graph representing exponential decay will decrease from left to right. So exponential growth, you're looking for an increasing line. Exponential decay, you're looking for a decreasing line from left to right. Real-world situations will more explicitly state whether growth or decay is occurring. So determine if the exponential function shows growth or decay. So for this one, our b value is 3. That is greater than 1, so it is growth. In this one, our b value is 1/3, which is between 0 and 1, which means it is decay. 0.28 is between 0 and 1, so we have decay. 1.78 is greater than 1, so we have growth. And then for this graph, it is increasing from left to right, so it is growth. And in this graph, we are decreasing from left to right, so we have decay.
Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.